What an unsettling recording start noise. All right, so I assume everybody got 100% on the quiz? Who forgot to study for it? You remember, I warned you, right? I don't even think it was a warning. I specifically said we're having a quiz. All right, good. What about the night before? What kind of sickness are we talking about? Oh, that's okay. Okay, well, you're conscious and stuff. You couldn't have. How long did they keep you waiting at the hospital?
Like 5 hours. It was a long time.
All right, well, it was plenty of time to study.
Like learn to write that stuff out on paper.
Just killing me. Okay, so last time we were messing around with doing this stuff from the command line, right? Which I said is the old school way of doing this crap. What do they call it? Oh, hello. All right, so, well, this is almost a solution. We'll write it another thing. But when we went to compile this, we saved it. We ran it through the Java compiler. It compiled, then we ran it through the Java virtual machine, and we got our output. In this case, our output would be, whatever command line arguments we gave. We were talking about that last time. Now, that would have been the old way of doing it, where you would go and you would edit a file in like a text editor, go and compile it, test, then run it and test to see how it worked. Kind of two different levels in there. You compile it and sometimes get errors. Sometimes you compile it and not get any errors, which means that what you wrote was syntactically correct, but it might not be logically correct. So what you wrote might not actually solve the problem you were trying to solve. So then you got to go back and edit it and save it, compile it and run it and blah, 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 all back and forth, back and forth, back and forth. Well, we have these things called integrated development environments, IDEs. Integrated development environment. Somebody want to get the front lights, the second to the top button? Thank you. See, I was actually talking to my wife last night, and we decided it was good that we don't have school on Monday. It was a Labor Day, because when students come back to school, you guys bring all these diseases from summer break, and the faculty all get sick the first week. You guys are terrible. So, like, he's congested. I got coughers over there. He thinks he has strep. I've been taking emergency. It was like just a bunch of vitamin C. Just every single day, I'm drinking it like Gatorade. I'll still get sick. Okay, so integrated development environment. Like a text editor on steroids. So what do these things do for you? Let's see. Color code, our source code. Auto indent. If I go back here real quick and I bring this back up. Notice how I've indented this so it's kind of easy to read. Well, I had to do that manually. And one of the problems that beginning programmers run into is they don't take the time to actually structure their code so that it looks nice. And it's not just for looks, it also helps you debug the program. You can see where the beginning of this starts and when the end of it is. Where the beginning of this one is and where the end of it is, so on and so forth. So indenting is actually a pretty important part of programming. It's not just for show. Well, our IDEs do this for us. They auto-indent. By default, most of the IDEs actually auto-indent in the way that I don't like, and I'll talk about that here in a few minutes, but it doesn't really matter. You can do it whatever way you want, as long as you're doing something with it. They also have built-in compiler/run. All right, so instead of text editor, typing javac, whatever the name of it is, then typing Java space whatever it is, you type it, hit the play button, just like a DVD player. All right, so we are going to be using an IDE in here called Eclipse. Website for this is eclipse.org. All right, so when you go to this website, it's free, first of all. You'll click download. What you want is the Eclipse IDE for Java developers. Okay, notice there's a whole bunch of them in here. There's one for C++ and PHP and all this other stuff. You got the full suite up here. Well, the one you want is the one for Java developers. Okay? So you'll download that for your platform. Notice it's noticed that I'm on a Mac right now, so it automatically selected Mac OS X. It doesn't matter which of these two you download. They'll both work on any modern Mac. There's a place in here where I can switch it to, oh, here we go. So you can get it for Windows, you can get it for Linux. Okay? And this will install it to, well, it'll download a zip file to your computer, and you unzip it, and it's all self-contained. There isn't an installer. So you just run Eclipse out of that folder. Because Eclipse, as I mentioned last time, is written in Java. So it's platform independent. It doesn't matter which, I mentioned that last time, right? Okay. It's platform independent because it's written in Java, so that's why it's available for Mac, Windows, and Linux all at once. All right. So you'll want to get that as soon as possible. I'm going to give you a homework assignment today that you'll need to utilize Eclipse for. So make sure you go and get that. Once you download it, you put it somewhere. For instance, on my machine, I unzip it and I usually drop it in my applications folder, but you can put it wherever you want. So here's the Eclipse folder. Looks like this. Here's your icon. I typically drag it out to my quick bar here, but you can do whatever you want. You can run it just out of the folder. It doesn't matter. All right. So I'm going to go ahead and open up Eclipse. And if you happen to already have Eclipse installed on your machine, it's an older version, it's really not the end of the world. You can download the newest one, but it's still going to work for anything we're going to do. Okay, so Eclipse is going to open. When it opens for the first time, something that's going to pop up is your workspace. Something like this will pop up, asking you where you want your default workspace to be. This is where it should save your Java projects. Now, where should your workspace be? Where should your workspace be on your computer? This is where all your homework will get saved. No, not wherever you want. There's got to be more. This is a computer science student quiz right here, verbal. Where should you put it? No. Go ahead.
Somewhere you can find it.
Okay, well, that would be a true statement.
External drive.
Huh?
External.
Okay, why an external drive?
In case your computer decides to commit suicide.
Okay. Well, but what if your external drive commits suicide?
Put it in the cloud.
Oh, in the cloud. Which cloud would you recommend using?
Well, I mean, there's anybody Dropbox.
Dropbox. Dropbox. Dropbox. Okay. I know I asked last time, but all of you should go to Dropbox.com. Sign up for a free account. It's free. No credit card. You don't have to put crap in. Okay? You get 2 gigabytes for free. Download it to your machine, install it. You'll get this little thing up here. See how there's a green check mark up there? That means everything. I always save everything that I don't want to lose inside Dropbox. That means if right now somebody came up here and sawed my laptop in half, I have not lost data. It's all in the cloud. So make sure that you install Dropbox and that you set your workspace somewhere in Dropbox. That way when you're doing your homework and you save stuff, it automatically gets synced to the cloud so that if your machine commits suicide, all you have to do is reinstall the OS, install Dropbox, and it'll sync all your crap back down. You've lost nothing. Hey, as computer science majors and minors, there's no excuse for losing data. No excuse. Unless you come to me and you say that there was some sort of cyber attack and the 4 computers that you have Dropbox installed on and Dropbox servers themselves were all simultaneously attacked and they all were destroyed. Now you've lost all your data. I would accept that as an excuse. Okay? So, Dropbox. Okay. If you happen to have an alternative solution like Dropbox, that's acceptable as well. But have some sort of cloud storage. It makes no sense. You can't complain it's too expensive. It's free. Okay. So, once you select your workspace, there's a little button on there. You can say, don't ask me again. This is where I want it to be. That's how I have mine set up. But choose some place that you want as long as it's inside your Dropbox folder. Anything you put inside the Dropbox folder will automatically get synced to the cloud. Okay? Only stuff you put inside the Dropbox folder. Now, what we're going to do is we're going to go ahead and create our Hello World program inside of Eclipse. So we're going to go through the process of creating a new project. So these are all existing projects that I've done for some other classes. So I'm going to go up to File. I'm going to say New. I'm going to say Java Project. Interestingly enough, if you get into Android development, you'll also use Eclipse for Android development. So, project name, we're going to call this CSC250 Fall 2014, just so I can differentiate you from my other classes that might be in here. You can call your project whatever you'd like. So I'm going to go ahead and hit Finish, and that's going to create kind of a new folder over here. All right. And if I double click in that folder, notice that we have a couple of different things in here. We have a folder called Source that has nothing in it. And then we have this JRE system library. That's the Java runtime environment. That's the Java virtual machine. You don't have to worry about that. It's there so your stuff works. Okay? You don't have to deal with it. But we want to add something to our source. So I'm going to go ahead and right click on Source, click New, and we're going to create a class. Remember last time we talked about how the Hello World program is put together. So all Java programs have a class. Inside the class, you have methods. And one method we've looked at so far is the main method. So we're going to create a new class, and we're going to go ahead and name this guy, well, here, we'll name it the same thing as we had our one out the command line, HW. So we'll go ahead and click Finish. Now, well, first of all, I'm going to point a couple things out here. So I hit HW. By default, it's set up as public, which we are going to need because the program that has main in it, the class that has main in it, must be public. Something here called superclass will default to java.lang.object. That's also correct. Second half of the semester, we'll be talking more about that, so just don't change it. Now, there's some things it will automatically do for you down here. And one box you can check is to automatically create the main method for you. But we don't need that because we already have it memorized. We just took a quiz on it, right? So we're not going to have them do that for us. And we're going to click Finish, and it's going to give us our empty program. Now, this is what I was saying about how the indentation, I don't really like the format they use. I don't like when you have the curly brace up on the same line as this. I like it underneath. I don't care how you write yours. I'm just telling you my personal preference is like this because that way you can see in a block structure the end and the beginning as opposed to that. Okay? Really, the reason that this syntax became popular is for books. You save a line when you see source code inside of a textbook. Okay? So I'll always just kick it down there. Do what you want, but no. And notice when I went from this line to that line, it automatically indented for me. So I'm going to go ahead and create my method, public static void main string array elephant. And then we'll do our system.out. Ooh, hello. Now, notice something else that's happening here. So I typed in system, then when I hit the period, it popped up a list of options for me. This is command completion. We'll talk more about that later because we don't know any commands at this point. But system.out.println, what's nice about it is it makes it so you don't misspell things. All right, so there is our hello world program, and then the equivalent of what we did last time is just hitting play. There's our output. So if you can run a DVD player, you can run Eclipse. Makes it nice and convenient. Okay, so questions about Eclipse? Go ahead.
Is it available for XP?
Sure. I don't know why it wouldn't be. Yeah, I mean, it says Windows. Did it say anything special on there?
No, I didn't say anything.
Yeah, I mean, I think it'll run on XP.
Alright.
You're still on XP?
I have a laptop that's on XP.
Okay. Yeah, I don't envision you running into any problems. Yeah.
Does it come with the Java virtual machine?
Yeah, it should be all self-contained. Okay. I believe it's all self-contained. If there's a licensing problem, it'll. There's tutorials on Eclipse in here.
I went to download it yesterday, and I think I downloaded standard instead of.
Yeah, the standard will throw your error for JVM, but the developer package won't.
Oh, this one already has the JVM in it.
Okay.
Okay. So, any other questions on Eclipse? You all need to have Eclipse installed and working. Your assignment that I'm going to give you at the end of the day today will involve doing your first assignment in Eclipse. Okay? So, let's see where I left off here. Okay. I think we already had this on a slide, didn't we? Yep. So how do human beings solve problems? Memory, asking questions, and repetition. All right, so all programming languages are going to give us tools which emulate the way human beings solve problems. So this is going to be another review from last semester, but I'm sure all of you have forgotten it. Variables. So this is how programming languages emulate memory. Okay, programming languages emulate memory through variables. Variables come in two flavors. We have primitive type variables, and we have object type variables. And we're not going to talk about objects quite yet. Probably next week sometime we'll talk about our first object. We're not going to write our own objects until, I don't know, midterm-ish, something like that. But in any case, these are the two broad classifications of variables. What we're going to be messing with most of the time for the next, well, at least for the next week or so, and then even after that, probably a large percentage of the time, is going to be our primitive types. From last semester, does anybody remember what a primitive type is? What is a only capable of holding a value. So our primitive type variable is a variable built into the language that is only capable of holding a single value. So this is built into the language and only capable of holding a single value. Anybody remember what the primitive types are in C-based languages? Go ahead.
Integer, string,
Not string. Int, char.
double.
I like your complete arbitrary order here.
I know I'm spacing around. Can't think of other ones.
Who? Float. Boolean. We're missing just one.
String.
Not string. Strings are object types. It'll be the first object we look at, but I'm not looking at those yet.
Short.
Short. Okay, so let's talk about each of these guys, and we're going to put them in a more appropriate order. Again, this is a review, and we'll see how much you remember. So we're going to say byte, short, int, long, char, float, double, Boolean. Out of these, the only one that varies between our C-based languages is Boolean. In Java, it's Boolean spelled that way. C#, it's bool. Objective-C, it's Boolean with a capital B. I think that's about it. But Boolean values are values that are just true or false. Okay, that's the kind of values that Booleans hold, true or false. And in the earlier days, this was 1 or 0. So behind the scenes, these are actually represented as numbers, and we'll actually talk about that here in a few minutes. Okay, but we think of them as true or false. Objective-C, the iPhone programming language, the Apple programming language, actually refers to them as yes or no instead of true or false. So it's digital logic, one or the other. All right, so let's go and talk about each of these. So each of these are a primitive type variable, and they're each built to hold a specific kind of value. Remember that Java, as is C#, as is C++, as is C, are all strongly typed languages, which means when we create a variable, we must specify the kind of values built to hold in those variables. We specify it this way by saying, I'm going to build a variable of type byte, or of type long, or of type char. Okay, so bytes hold whole integer values. Shorts hold whole integer values. Ints hold whole integer values. Longs hold whole integer values. Chars hold whole integer values. Okay, that seems like kind of a waste. So we have 5 different primitive types that all hold the same kind of crap. So how do these guys differ? These first 4, byte, short, int, long. How are they different from each other?
The amount of it is
Size.
What they can hold.
Yeah.
So, and actually I'm going to add something to each of these. These are all signed. Which means they can hold positive and negative values. As opposed to an unsigned value, which would be only positive. And that'll make more sense here in a second. Okay, so all these first 4, actually, sorry, small little error here. For char, that's actually an unsigned integer. All the other ones are signed. Okay, so for the first 4, these are all whole signed integer values. And as you pointed out, the difference between them is the size of the values they can hold. A byte is a signed 8-bit integer. a short is a signed 16-bit integer. An int is a signed 32-bit integer. A long is a signed 64-bit integer. And we'll get to this in a second, but a char is an unsigned 16-bit integer. All right, so what does this mean in terms of real values? A byte can hold values in the range of -127 to +128. That's the range of values you can store inside of a signed 8-bit integer. Why is that? Let's kick it over to another screen. What's a bit? One or a zero. A bit is a 1 or a 0. So 8 bits would be 8 ones or zeros, right? So like that would be a byte. 8 of those guys, right? So the range of values for these guys is in that range. Now, how do I read these? You guys dealt with binary numbers in 150, right? I know you dealt with it in the 200 class. So how do we write the number 1 in binary? Number 1 is that. If we're going to represent it as an entire byte, it would be that. What's the number 2? What's the number 3? All right, so how do these guys actually work? Work like that. Now, underneath these, close enough. This is the ones place. This is the twos place. This is the fours place. 8s, 16s, 32s, 64s, 128. So, the number 1 means we have a 1 in the ones place, plus a 0 in the twos place, plus a 0 in the fours place, plus a 0 in the eights place, plus a 0 in the 16s place, plus a 0 in the 32, plus a 0 in the 64, plus a 0 in the 128s. So 0 times 128 is 0, plus 0 times 64 is 0, blah, 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 plus 1 times 1 is 1. Add it all up, you get a 1. The 3 would be 2 times 1 is 2, plus 1 times 1 is 1, 2 plus 1 is 3. That's how we convert between binary and decimal. Okay? Now, this is nothing new to us. And what I mean by that is if this was the decimal number 21, this is the ones place, this is the tens place for base 10, for decimal numbers, right? So 1 times 1 is 1, plus 10 times 2 is 20. 20 plus 1 is 21. Does that make sense? So all we've changed is the base. If we add another, ooh, hello. We add another bucket on here. This is the hundredths place, right? So 421 would be 4 times 100, which is 400, plus 2 times 10, which is 20, plus 1 times 1, which is 1, which is 421. Make sense? What if I said we were dealing with octal, base 8? What would these numbers be for base 8? Well, this would still be the ones place. This would be the eights place. What would this place be? 64. We just keep multiplying by 8. This one, base 10, we keep multiplying by 10. 1, 10, 100, 1,000. Base 2, we keep multiplying by 2. 1, 2, 4, 8. Base 8, we keep multiplying by 8. Base 16, kind of our other common one, is hexadecimal. We'd multiply by 16. All right? So, computers. Hello. Computers like binary numbers. Why is that? What's good about binary versus decimal? Okay, why is that good for a computer?
You can only that's the only way it works is on 2 options, on or off. For the circuits.
Okay. Well, why is that the only way it works? It kind of becomes a little bit of a computer architecture type question, but just to give us a little filler backstory here.
Switches.
What integrated circuits, transistors. Okay, specifically transistors. When you guys took 150, you saw the gigantic computers, UNIVAC, EDVAC, that had the vacuum tubes. A vacuum would look like big light bulbs, right? Light bulb is either on or off. Okay, so we represent numbers as a whole bunch of individual bits, on or off. How would we represent, if we used a computer, use those vacuum tubes to represent the decimal number 21, what would we have to do? How would you represent 21 using vacuum tubes? Just 21 vacuum tubes? Okay. Well, how do you represent the number 1,363? Even more vacuum tubes. Okay. So we could do maybe that's the reason they were the size of a gymnasium, right? So even if you took a computer and you made it the size of a gymnasium, you're still going to have a fairly finite maximum number size, right? That won't be anywhere nearly as impressively large as it should be, right? Because it's decimal. How do we represent the number 21 in binary? Well, we'd have a 1 in the 16th place, 1 in the 4th place. So it's 10101. That's the number 21, as opposed to 21 vacuum tubes. What's your suggestion? Okay, so it's a little bit better. So we can support the number 21 in 8 bits, correct? Now, what's the largest decimal value that 8 bits can represent? These are all ones. So that's 1. That's 1. 1. 256? 255? Well, which is it? Well, we have 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. 255. So what's the range of values we can represent using an 8-bit number? What's the smallest value we can represent? 0. All zeros. Yeah, we don't even have to have 1 1 in there. So the range of values in an unsigned 8-bit number is 0 to 255. But a signed number, we need to be able to hold positive and negative numbers. So we need to actually use one of those bits to keep track of whether it's positive or negative. So this guy down here, this last bit, no longer becomes part of the number. Now it's part of the sign. Okay? So that means that we really only have 7 bits here for representing the actual value. What's the largest positive number we can support using a 7-bit number? 127. So the range of values that can be represented by a signed number is negative 128 to positive 127. Okay, there's something called 2's complement that we deal with at a different point in time. That is where we get the extra 1 on the negative side. So there's our, and actually I lied to you here. Negative 128 to positive 127. That's the range of values by an unsigned byte. So even though it's an 8-bit integer, only 7 of those bits are used for numbers. And you'll actually find this is negative 2 to the 7th power to positive 2 to the 7th power, minus 1. A short, same exact idea, except we have 16 bits. Range of values are negative 32,768 to positive 32,767. An int, plus or minus 2 billion. As I always say, my precision starts going downhill as we get to larger and larger numbers. And then a long is plus or minus big number. It's something like 16 quadrillion, blah, blah, blah. Okay? And you can do the math. This is plus or minus 2 to the 7th. This is plus or minus 2 to the 15th. This is plus or minus 2 to the 31st. This is plus or minus 2 to the 63rd power. To get, if you want those actual, actually I'm interested here. Is the 2 to the 63rd, does that actually give me a value? Yeah, look, there we go. It's plus or minus that. That's a long. Now, if you didn't know this, it's a trick on a Mac. You can use Spotlight to do math instead of bringing up a calculator. I was more interested if the little caret thing worked for powers. Yeah, so that's, yeah, it's a big number. So I'm pretty accurate here when I said big number. All right. Now, notice a char is unsigned, which means we do not need to use that bit, that first bit for the sign of the value. We get to use all, in this case, 16 bits. So what's the range of values that fit inside of a char? A char is the same size as a short, but without the sign. So what's the smallest value a char can hold? 0. To 65,535. It's the range of values that fit into a char. Let's throw a slide on here. We have something called Unicode. What? Did I spell that right? I'm very proud of myself. First try. Successor to ASCII. Anybody know what ASCII stands for? Is that a 150 thing?
American Standard Code for Information Interchange.
It does. American Standard Code for Information Interchange. Okay, and what was ASCII used for?
Wasn't it one time used for websites?
We'll say this again.
Like websites?
Okay, what about them on websites?
Like where they put like pictures and things?
To make make the pictures?
Like, yeah.
I think you're thinking ANSI.
Okay.
ANSI graphics. Like if you played old like text-based games that had pretty graphics on them, something was called a MUD. That was called ANSI. ASCII.
Isn't it like the letters? Yeah, there's a number code for a letter. Great words.
Every letter, every American character, what we'll consider to be American characters, had a code associated with it, had number associated with it. Okay? But then what happened is we decided, by the way, not everybody speaks English. I mean, I agree they should, because that's all I speak. And why should I have to learn another language, right? And actually, the world has become that, right? You go anywhere in the world, they all speak English now just to deal with the dumb Americans.
You have to force them to actually speak their language if you want to practice.
Say this again.
When I was in Germany, you had to force them to speak German if you wanted to practice German.
Oh, you had to force them to do it?
They would not.
Oh, because you were trying to learn German.
Yeah.
Yeah, I know enough German to order at Mater's German restaurant. Yeah, that's my feeling. As long as you can ask where the bathroom is, and you can order at the restaurants, you know enough of that language. And actually, interesting, twist off of that. There's a newer restaurant here in Mequon called, the main company is called Zarletti. It's an Italian restaurant, and it's over by Cafe 1505 or off of Mequon Road. Their entire menu's in Italian. Okay, now I'm kind of a foodie. I go out to a lot of kind of fancy places and order the weird crap. And my wife and I had to Google this entire menu. We had no idea. You order a pasta at a place, and usually you kind of recognize your kind of standard fare of pastas, right? You got your fettuccine noodles, you got your spaghetti noodles, your cavatappi. Well, that starts getting a little fancier, right? I didn't recognize one noodle on this menu. It was ridiculous. They should have just drawn pictures. What was it? Oh, Unicode. Okay. So, ASCII was 0 to 255 unique characters. So we had 256 unique characters represented in the ASCII character set. So this is our whole alphabet, upper and lowercase. This is all of our numbers. This is all of our punctuation. And then we had some other things, American filler, like we had smiley faces, we had some of the playing cards. Things that we obviously do, like emojis, right? But yeah, that was actually part of, it's like, oh, we don't want to include other languages in here. Let's just put pictures. All right, so Unicode is a superset of ASCII. That is the first 256 characters of Unicode. It's a mapping. Unicode and ASCII are mapping. So you map from a number to a character and vice versa. Because computers like numbers. Unicode's a superset of ASCII. So the first 256 characters of Unicode are the 256 characters of ASCII. Then after that, you have all these other languages in there. Okay? So Unicode is 0 to 535 unique characters. So that's 65,536 unique characters. Okay? Actually, here we can do a quick little experiment. Let me go to preferences. think that should be good. So just as a fun experiment, let's print out. I need to do something here. I want to make sure I have ASCII turned on. Oh, UTF-8, it's fine. That's ASCII. So we're going to look at the characters from the ASCII character set. So for int I is equal to 0, and don't worry, this is another one of those loops that we don't know yet. I is less than 256. And I think I have this thing configured where we'll show these characters. So these are all the ASCII characters. Yeah, the question marks mean it didn't know how to deal with it. Didn't know how to display it. Let's see if I can fix that a little bit.
Gotta make sure you have that Korean.
Oh, non-lossy ASCII. Here, let's just enable all. That's bound to be a catch-all, right? Have to reset it, maybe?
You have to compile again.
No. No, there's not. I've seen. There's literally smiley faces and stuff. I've seen them.
You have to restart the program first.
That's what I'm wondering. Oh, here, character. Oh, that's for international. It's fine. Yeah, let's try restarting it and see if we get our pretty pictures. No, we don't. Oh well. It's going to show you playing cards and stuff like that. Just trust me, they're there. Huh? You can, but that wouldn't have been as fun.
Oh, right.
We had a program to print them. Google.
Try it in Eclipse.
What's up?
Try it in.
No, it's even worse in Eclipse.
Yeah.
Eclipse will have far more of the question marks. The built-in terminal only knows certain stuff. Okay. In any case, Unicode supports 65,536 unique characters across many languages, natural languages. I won't say all of them because I'm sure we're missing some, but there's like surprisingly like awkward, weird, languages spoken by 3 people in the world are built in there. Okay, so a char is an unsigned 16-bit integer, 0 to 65,535, where each character of a char is actually stored as a number. Proof of that, here we'll come into Eclipse. I'll start writing this stuff in Eclipse for our proof. All right, so when I run this is going to print out the whole alphabet, lowercase. And we'll see that, blah, blah, blah. So there's our alphabet. Now, because C is a char, remember, Java is a strongly typed language. Because I've advertised that this variable C is holding chars, when I print it out, it does the conversion for me. It maps it to a char. So I get the actual letter. But if I force it to print out the integer version of that, if I force it to do that, it's going to give me the actual Unicode values of those. So A is a 97, B is a 98, so they're all next to each other. Make sense? We'll see uppercase letters. Come before the lowercase ones. So that's 65 to 90. All right, makes sense? So that's kind of our evidence that in Java, chars are actually represented as numbers. They are just displayed as characters. All right, so chars, an unsigned 16-bit integer. Floats are signed 32-bit by 32-bit decimal numbers. A double is a signed 32-bit signed 64-bit dot 32-bit decimal number. So after the decimal point, it's 32 bits of precision. Before the decimal point, doubles can hold 64-bit numbers like longs. Floats can hold 32-bit numbers like ints. Now, question. Why do we need so many different ways of holding integers and doubles, or integers and floats? Why wouldn't we just always use a long? Figure, well, it's got to be big enough for pretty much everything. If we run out of space, then we'll just go to objects. I'm telling you that some objects allow us to do arbitrary size integers. But why do we have all these choices? Go ahead.
For speed, it has to go through every single integer, even if it is marked as a 0. It has to read all of them. So if you have something that you only need 8 bits for, just write that in the computing power.
Do you actually think that we would notice a difference?
I'm just saying.
Yeah, I think speed is, by today's standards, is a pretty crappy argument. Our computers are so fast, we wouldn't even notice. And beyond that, our compiler technology, when we compile a program, when we turn it from a high-level language to a low-level language, if the compiler can sort out that the largest number you ever store in something is a 10, it'll convert your ints to bytes. It'll do that, the smart stuff for you. So one of the, if you were to generically say what's the job of a compiler, we might say make bad programmers look like better programmers. Okay? So, I mean, speed's not an unreasonable answer. It's just not, you know, it's not really a valid answer from our human perspective of computing. Math happens so fast in these computers, and I mean, do we care if it's taking it, 6 nanoseconds rather than 4 nanoseconds? As long as our email pops up, right? We don't care. Okay, so why else? Go ahead.
I don't know if this is really an argument anymore either, but I was going to say memory space.
Okay. It's actually the correct answer, and everybody in here should have known that from last semester, but let's go ahead and go with it. So tell me why.
Because you can, as fast as your processor is, you can only run multiple, well, you used to only be able to run one thread at a single time. Now you can run multiple threads at a single time, which is basically allowing you to run like singular actions single time, even though it's very fast. That's not a very good way to
Yeah, so I mean, the longer you've babbled now, the worse your answer becomes, actually. So,
One just takes up more space than the other.
okay, that's a true statement. But why do we care about space? How many of you have a hard drive smaller than 1 terabyte in here? On a desktop computer. Smaller than 1 terabyte? How old is this desktop?
Not that old, but I cheaped out. I built it myself and just knew I wasn't going to use terabytes.
Is it solid state?
Yeah, that's awesome.
Okay, well that's who in here has a desktop computer that has a hard drive smaller than 1 terabyte that's not a solid state drive? Solid state's a good argument because he bought a faster drive, but a 1 terabyte solid state drive is prohibitively expensive. A 1 terabyte mechanical drive is they almost give them away at McDonald's and stuff. They're free. They're basically free. Okay, so when you hear 1 terabyte hard drive, that doesn't impress anybody anymore, right? So how many longs, so 64-bit integers, can we store in a 1 terabyte hard drive?
Big number.
A lot, right? We don't need that many numbers. Okay, what about RAM? So let's talk about why your program's actually running, where the variables are actually stored. How many of you have more than 4 gigabytes of RAM in your computer?
Can we all just say that Randy wins because we know he does?
Oh, does he?
It's 32.
32 gigabytes.
You have 32 gigabytes? Okay.
I only have
Anybody have
16.
more than 32? Who has 16? 32 is in a desktop?
Yep.
Okay. Yeah, I think I have a server at home that has 32 gigs. I have 16 in my laptop. That's respectable, right? Okay, so we'll take his 32 gigs. Certainly above the norm. Actually, no, let's take our 4 gigs. Lots of you had 4 gigs, right? So I mean, these are. I mean, again, 4 gigs. When you get a new computer today, it probably comes with 8. You know, you would have to break part of your computer to have 4. How many longs can we store in 4 gigabytes? Answer again becomes big number. We'll break down gigabytes and all that crap here, probably next class. But generally speaking, big number, right? Okay. So do we care about space anymore? The problems we run into rarely have to do with space. With some exceptions. I mean, once you've downloaded literally the entire iTunes library illegally, maybe you fill up your 3 terabyte external drive. But now where are you going to put the movies? Right? On your other 3 terabyte drive. You know, then we got to deal with processing power because you got to convert them to some sort of codec that you can watch. So space and memory really aren't a problem today, but they used to be. And again, I'm repeating myself from last semester. How many of you have heard of the Y2k bug?
Mm-hmm.
What is that? What was the Y2k bug? Go ahead.
They ran out of years in their calendars, and so they were freaking out that their computers were gonna explode.
They ran out of years in their calendar?
Like when in the
The
calendar
Mayans?
when they were making the calendar application, they only went up to like 1999.
Oh, so we only had to fix the calendar application.
Well, and everything else, the calendar application was based off of.
Okay. Why was we're a little rocky here, but we're not horribly off course yet. So, why was there a problem? So the Y2k bug was when it goes from 1999 to 2000, computers weren't going to be able to, or at least some computer programs weren't going to be able to differentiate between the year 2000 and the year 1900 because they used 2-digit years, correct? Okay. Why was this a problem? Why didn't somebody think of this before that? Go ahead.
Was it like a memory saving measure?
Yeah, absolutely was a memory saving measure. Now, a lot of the software is written in, let's say, the 80s. I'll just use that as an example. So it's 1983, and you're a computer programmer. And how much memory is in your computer in 1983?
16 bits.
Megabytes? No way.
Kilobytes. 16 kilobytes.
Okay. 500 meg would have been 512 megabytes. 512 megabytes in 1983 was far, far, far more impressive than his 32 gigs. People would have joked like NASA didn't have 512 megabytes of memory. I mean, we're not even in the right realm. 16 bits is closer and probably high. Okay? Okay. Not a lot. All right. Not a lot of memory in our computers back then when the software was being written. So we had to use it wisely. Right? It's kind of like when you have to come to school and your car is a Geo Metro. Do they make those anymore? Is Geo still car? Pick your favorite tiny car. Cooper, a Mini Coupe? Mini Cooper? Okay. So you're going to bring all your dorm room crap to school in a Mini Cooper. You got to be selective, right? Yeah. You're not bringing your queen size bed from home. It's like, how much stuff can you stack on top of a Mini Cooper? It's got it bungeed, you got it duct taped. You actually have a friend you drive side by side and you create a bridge.
Nobody goes the motorcycles under the
Right, yeah, it's a whole ordeal just pulling in for food at McDonald's. One person has to go on the out, the other, it's a whole ordeal. But back then, when a computer programmer was writing something, they had to be extremely selective on how they used memory. We don't even think about it today. It's like, oh, well, I only need to store the numbers between 1 and 10. Well, that's an int. Realistically, programmers today, they use ints 97% of the time. I just pulled that out of the air, but it's probably pretty close to correct, if not low. If an int isn't long enough, they use a long. If a long isn't long enough, they go to one of the objects for holding arbitrary numbers, where you give up performance, but it can just hold anything. So that's on the integer side. On the floating point side, everybody just uses doubles. Nobody uses floats. So the question would be, why doesn't everybody just use longs? I don't know. They just don't. Convention is you use an int unless it's not big enough, and you use a double, done. If it's not big enough, then we're going over to objects. We don't care about space anymore. You know, your computer's got 32. What do you do with 32 gigabytes? I mean, is it bragging rights, or do you actually use this RAM for something?
No, it was more like a future-proofing kind of thing. Like, it was like, well, I have this extra money, you know, like when I was building my computer. I was like, I can either get like 16 gigs or I can get 32. It's only like $200.
But how's that future-proofing? By the time you need 32 gigabytes of RAM, that computer won't be able to do anything. It'd be like equivalent to like a broken sewing machine.
I don't know, like there's stuff that requires like 8 gigabytes of RAM. I'm sure that like in like a year or two, there's going to be stuff that's going to require 16.
This sounds like a Bitcoin bet to me. There is no way that you will ever use 32 gigabytes of RAM on that machine. Having said that, the nice thing about your situation is you can turn virtual memory completely off and gain some performance. Do you at least have a solid state drive? I got a 32 gigs of RAM. I have an 80-inch 4K monitor.
No solid state.
It cost more than the state of Kentucky. But I went with a 1 terabyte, 5,400 RPM mechanical drive. Okay, so these are our primitive types. In the old days, when programmers were writing their programs, we actually had to take size into consideration. That's why a lot of those programmers in the 80s chose to represent dates as 2-digit numbers to save space. Kind of thinking, well, I'm sure the problem will solve itself by the year 2000, or these programs are going to get rewritten by then anyways, or whatever. Just not a whole lot of foresight. They didn't future-proof. So anyways, that's why we have all these things. Remember, the parent language of this guy, of Java, is C. That guy's a much older language, okay? Back from even before the early 80s. So C++ got all of C's primitive types. Java got all of C++'s primitive types. So all the primitive types that existed in C still exist in Java. And that's why we have so many to choose from. Realistically speaking, you will hardly ever, well, here, you will definitely use booleans, you'll definitely use doubles, you'll definitely use chars, you'll definitely use ints and longs, and on occasion, you might use a byte not because of the size, but because you're manipulating video or something like that, and it's coming in 1 byte at a time. Just because it happens to be compatible with what you're doing. Not because you're like, well, I don't need to store a number bigger than 127. No, that's an int. All right? Your homework assignment for Friday is to download Eclipse and get a Hello World program working. Take a screenshot of it, upload it to Angel. I'll put the assignment up right now, but I want to see a screenshot of Eclipse with your code on it and it running.
So by tomorrow.
Right.
Oh, Tuesday, I'm sorry. Next class. I was thinking today was Wednesday. Thank you. By the beginning of next class, I want you to complete that. By noon.
Oh yeah, that's real great. So he